Section 12.5 on conditional probability. I want to talk about the idea of independent and dependent events. I alluded to that in the earlier formulas when I put up those formulas in advance. Independent events are ones for which the result of one event does not affect the probability of the occurrence of the other. There are some simple examples that we'll go through, but I need to throw up the thing to contrast it with, which are dependent events. Dependent events are one for which the occurrence of one event affects the probability of the occurrence of the other. Now that you can see the contrast, I want to put some examples up and see if I can make it even clearer. Let's decide whether the following events are dependent or independent. Doing your assignments and passing your math class. Do you think doing your assignments might have some effect on the probability of you passing your math class? Yeah, I think most people would agree to that. So those are dependent events. One thing can affect the probability of the other thing. How about this? Running daily and winning the New York Marathon. Again, I think most people would agree that that might have an effect. That daily running might very well have an effect on how probable it is that that person will win the New York Marathon. So I'd say, again, those are dependent events. How about this? Winning the lottery and winning a spelling bee. It's really hard to imagine how winning a lottery could affect the probability of winning a spelling bee, or the probability of winning a spelling bee would have any effect on the probability of winning a lottery. So those two events are independent. Getting heads on a coin toss and rolling a 6 on the standard die. Flip a coin, does it matter what you get in terms of it changing the probability that you're going to roll a 6 on the standard die? No, I don't think so. So those are also independent events. This sort of gives you an example of what we mean by dependent and independent. You mainly need an intuitive idea of what they mean. How about this? Drawing an ace, then drawing a 2 from a deck of cards without replacement. Now think about this. If you draw an ace out, you don't replace it, and then you draw a 2, that does affect the probability, because since you didn't put that ace back in, you only drawing from 51 cards the second time. There is a dependence there. Drawing that ace out and not putting it back in makes those two events dependent. If you put the ace back in before you drew again, then that would erase the dependence and they would be independent events. These are very important distinctions. You need basically an intuitive idea, but having an intuitive idea is extremely important. And this leads to something called the product rule for independent events. If two events, E and F, are independent, then the probability of E and F is the probability of E times the probability of F. That was one of the tools that I flashed up at the very beginning and said we would get to it later. Suppose you flip two coins. What is the probability that the first flip is heads and the second flip is tails? The coin flips are independent. What I get the first time I flip the coin has absolutely nothing to do with what I get the second time I flip the coin. So that means they're independent. So that tells me that the probability I get a head and then a tail is simply the probability I get a head times the probability I get a tail, because that's what the product rule for independent events says. Well, the probability I get a head is 1/2. The probability I get a tail is 1/2. So the probability I get a head followed by a tail is 1/4. A half times a half. That's the product rule for independent events. Just want to say that you could have worked this problem with a tree diagram. If you look at your first toss as being the first stage of a two-stage experiment, the probability of getting a head is 1/2. And then once you've done a head, the probability of getting another head is 1/2, but the probability of getting a tail is also 1/2. So if you look at the branch that goes from heads to tails, you see it's 1/2 probability you get a head, and there's 1/2 probability you get a tail. And we learned earlier that the probability multiplying down a branch is the and probability. So the probability of getting a head and a tail, where the first is a head and the second's a tail, it would be 1/2 times 1/2, which is 1/4. So we did learn something in earlier sections that would allow you to get that same answer with a tree diagram. But treating it as just two independent events is much simpler. Now I want to talk about conditional events. That's the subject of section 12.5. And this is also where I said earlier we introduced some new notation. The conditional probability of event E occurring given that event F has occurred is the probability of the event E occurring taking into account that event F has already occurred. And that's what the adjective conditional means. Conditional probability means the probability conditioned on the fact that something else has already occurred. It's good probably to introduce this idea through an example. Let's let E be the event that the sum is 5 when we're rolling 2 dice. What is the probability of E? Well, that's just the probability we get a sum of 5, and we know how to do that. We draw our 2x2 table, and we count the sums that come to 5, which happen to be 4, and we get, by the basic probability principle, it's the number of ways of getting what you're looking for, which in this case is a sum of 5, divided by the number of ways you can get anything in the sample space, which we know there are 36 things, so it would be 4 over 36. If you want to reduce it to 1/9, you can. But what if I tell you that I've already peaked? I've done the die roll already, and I'm holding my hand so you can't see it, but I've peaked, and I'm telling you something about it. I'm not telling you what the sum is, but I'm going to tell you, well, I'm not telling you what it is, but it's odd. Does that matter? Does that change the probabilities because I gave you some new information? And the answer is, in general, yes, that will make a difference. So what I really want now is the probability the event E happens, which is getting a sum of 5, given that additional information, given that the sum is odd. That additional information is important because if I know the sum is odd, that changes the sample space because I don't have to consider any even sums anymore. So I can get rid of every sum that comes out even. 1 plus 1 is 2, that's even. 5 plus 3 is 8, that's even. 5 plus 5 is 10, that's even. 6 plus 6 is 12, that's even. So I can get rid of all of those. So that additional information is extremely useful. I can throw out the things that no longer contend because I know it's odd. The evens don't contend anymore. So the probability of E, given that the sum is odd, is just the number of ways that E can happen with that new condition, in this case that the sum is odd, divided by how the sample space changes given that new condition. So you're still doing a count of the event E, and you're still doing a count of the event S, but you're taking into consideration that something has happened and you have more information than you had to start with. That's what I mean when I say with condition. Well, once I crossed out all the even sums, there were 36, half of the sums were even. That knocks the sample space down to 18. There are only 18 odd sums. And then I look, none of these sums adding to 5 got knocked out because they were all odd, so there's still 4 of those. So the probability of the sum being 5, if I know that the sum was odd, is going to be 4/18. It would have been 4/36 had I not known that. So instead of the probability of the sum being 5 being 1/9, now the probability that the sum is 5 with that additional knowledge, that knowledge being that the sum was odd, now has doubled to 2/9. Yes, it does matter, or at least it can matter. You can see here the probability doubled. Knowing that information doubled the probability. So, to sum up, when we have a probability which includes an extra condition, and in this problem it was that the sum was odd, that probability is called a conditional probability, and we have a special notation for it. And if we go back to that previous example, the probability of E, I just wrote this sort of intuitively. The probability of E, comma, given that the sum is odd, we're going to modify that. I just wrote that out kind of intuitively. Suppose we call that condition F. In other words, the sum being odd is a new condition called F. So the sum being 5 was the event E. Now we're going to call the sum being odd the condition F. Then we'd write the conditional probability with this vertical line. The probability of E, and the vertical line is read as given that. So that's the probability of E given F. So that new notation, the vertical line is read given. So this is the probability of E given F. or given that F has occurred. Probability of E given F. That's conditional probability. This is important, so take a minute to just soak it in. The probability of E given F is the conditional probability of event E given that F has occurred. That F is the additional information that we now know that we didn't know before. The vertical line is read given or given that, depending on exactly how you want to phrase it. For our particular problem, this would be the probability that the sum is 5 given that the sum is odd. Think about that a minute, because you need to understand what the probability is saying or asking before you can get an answer. And if I don't make any other point in this lecture, I want to say this and make this point. Oftentimes, if you understand how the given that condition restricts the sample space, the original sample space, you can solve this conditional probability problem without even formally using formulas. But if you really understand how the given that condition restricts the original sample space, quite often you don't really even need formulas. For example, if I told you that 2 cards are drawn without replacement from an ordinary deck of cards and asked you the probability that the second card is a heart given that the first card was a heart, they're asking me for the probability the second card is a heart given that the first was a heart. Well, if I know that the first was a heart, I'm given that the first card was a heart, then that reduces my sample space. If I know the first card was a heart, when I draw again, instead of having 52 cards in the deck, I'll only have 51 cards in the deck. And since the first card was a heart and there are 13 hearts in the deck, if the first card really was a heart, after I draw a heart out, I only have 12 left. So knowing that the first card was a heart, if I didn't put the card back and it says drawing without replacement, when I draw again, or just before I draw again, I'll be drawing from a 51 card deck that only has 12 hearts. So now the probability of that second card being a heart is simply 12 out of 51. Knowing that the first card was a heart and that it wasn't replaced reduced the sample space down to 51 cards, 12 of them being hearts, and that probability would be 12 out of 51. Simple if you know how to think about it. And if you want to reduce that to 4/17, you can. How about this one? A container has 35 green marbles, 20 blue, and 4 red marbles. 2 marbles are randomly selected without replacement. If E is the event that a green marble is selected first and F is the event that the second marble is not green, compute the probability of F given E. I will say that when I see these problems where the events are given letter names, if they tell me what the actual events are, my inclination is to go ahead and replace the letters with an actual phrase representing the event. So if F is the event that the second is not green, I'll just write that out. And if E is the probability that the first was green, I will just write that out. It's up to you, but I think it's easier if you do it that way. Now, having done that, remember, we're given that the first draw resulted in a green marble, and we're doing it without replacement. So if there started off being 59 marbles, after the first draw there are only 58 marbles, and the one that was drawn was a green. So instead of 35, there are 34 green. We want to calculate the probability that the second was not green, given that the first was green. You can see that I've already put the answer up there as being 24 over 58, and I think you can see that where that came from. The denominator is simply the count of how many marbles were left, and the numerator are the number of things that are not green, a number of marbles not green, and you can see that there are 20 blue and 4 red, and 20 plus 4 is 24. So there were 24 non-greens to choose from. So the probability is 24 over 58, non-greens over total marbles left. And it's 58 instead of 59 because you were drawing without replacement. If you want to reduce that, you can reduce it to 12/29, but WebAssign really doesn't care. How about this one? 2 dice a roll. What is the probability that the sum of the dice is 6 given that the roll was a double? Again, you want your sample space in a table 2 by 2, 6 possibilities for the first roll, 6 possibilities for the second roll. You're given that the roll was a double. So we want the sum to be 6 with the additional information that we rolled a double. So the probability that the sum is 6 given that the roll was a double. Well, if we know the roll is a double, we know that's already occurred, we can get rid of everything but the doubles. Well, the doubles are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So all of a sudden that 36 member sample space reduced down to 6 because we know that it was a double. So we'll be dividing by 6. Out of those remaining 6 choices, only one has a sum of 6, and that's 3, 3. 3 plus 3 is 6, so the probability is 1 out of 6, or 1/6. See how this works? If you can think it through, you don't really have to memorize the definitions. You just have to understand what the condition does to the sample space. How about this one? Mrs. Fraga's class has 109 students classified by year and gender. It's listed in the table below. She randomly chooses one student to collect homework. What's the probability of selecting a female given that she chooses randomly from only the sophomores? So the given that part is that she's only choosing from the sophomores. That means you can eliminate all the freshmen, all the juniors, all the seniors. So your sample space has reduced down to just the 21 sophomores. So now what's the probability of selecting a female? Well, look within the remaining choices, those 21 remaining choices, 5 of them are female out of the 21 sophomores. And notice again, I said it, but I'll actually write it. There are 21 sophomores, so the probability that the student was female, given that the person was a sophomore, is going to be the number of females over the remaining things in the sample space, which are just 21 sophomores. So your answer is 5/21. Very simple if you understand what you're trying to do. This might be a good place to mention that we can use the conditional probability ideas to modify the product rule for independent events that we've talked about earlier to handle cases where the events are dependent, as we've been talking about. Recall that the product rule for independent events says if 2 events, E and F, are independent, then the probability of E and F is equal to the probability of E times the probability of F. But if the 2 events are dependent, we can modify that slightly to say that the probability of E and F is equal to the probability of E times the probability of F given E. It's still a product, but you're using that conditional probability. If 2 events, E and F, are dependent, then the probability of E and F is the probability of E times the probability of F given E. Let's do an example. Let's draw 2 cards from a standard deck of 52 without replacement. What's the probability that your first card is a spade and your second card is red? Recall your deck of cards. You have to know enough about a deck of cards to answer these sort of questions. The first card being a spade causes you to look at the deck of cards and realize that there are 13 spades in the deck. The second card being red causes you to look at the deck of cards and realize that 26 of those 52 cards are red. The product rule for dependent events says if 2 events, E and F, are dependent, then the probability of E and F is the probability of E times the probability of F given E. Here, that would be the probability of the first being a spade and the second being a red is equal to the probability that the first is a spade times the probability that the second is red, given that the first is a spade. And that should be easy enough to figure out. What is the probability that the first is a spade? Well, as we said, there are 13 spades in the deck, So the probability of drawing a spade on that first card is 13 50-seconds. Also keep in mind you could reduce 13 50-seconds to 1/4 if you want to. Don't necessarily have to, but you can. What about the probability of the second one being red given that the first one's a spade? This is a little tricky if you don't think, because you're drawing without replacement, which means if you draw out a spade, you're not putting it back in. So the deck now only has 12 spades and one less card, so that would be, instead of 52 cards in the deck, there would only be 51 in the deck. There are still 26 red cards, but now one of the cards has been taken out and not replaced, so there are only 51 cards left in the deck. So the probability of getting a second red, given that you've taken out a spade, is not 26 out of 52, but instead is 26 out of 51. And if you multiply 1 times 26 and 4 times 51, you'll get 26 over 204. And as I said, you could have left that 1/4 as 13 50-seconds. You did not have to simplify it, but it's nicer if you notice those sorts of things, I believe. So the answer will be 13 over 102 if you simplify it as much as you can. WebAssign doesn't really care if you simplify fractions, but if you want to, you can. How about this one? 3 cards are dealt from a well-shuffled standard deck of 52. What is the probability that the first card is red, the second card is black, and the third is red? And give your answer as a fraction. Remember, 52 cards in the deck. The deck of cards has hearts, diamonds, spades, and clubs. There are 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, and 10s, and then there's the jacks, queens, kings, which are the face cards, and then there are aces. 52 cards. The product rule says that the probability the first one's red and the second one's black and the third one's red is the probability the first one's red times the probability the second one's black, given that the first one was red, and times the probability the third one is red, given that the first two choices were made. So those last two are conditional probabilities. It's basically the probability of getting a red, the probability of getting a black, the probability of getting another red, but you're taking into consideration what's already been drawn out, because if you're dealing cards, they're not being put back in, so they're not going back in, so that means it's without replacement. That's what makes it a conditional probability. So anyway, we want to find out what is the probability of drawing that first card red. Well, there are 26 cards in the deck of 52, so that's 26 over 52. That also happens to be 1/2, so if you wanted to write it as 1/2, that's perfectly okay. I'll leave it that way for the time being. But what about drawing the second black? Now you've got to be careful. After that first card is dealt, it doesn't go back in, so there are only 51 cards left in the deck. I drew out a red, so there are only 25 reds and 26 blacks. So the probability of getting a second black from that deck of 51 cards is 26 out of 51. I want a black, and there are still 26 blacks in there, but there are only 51 cards in the deck. So the probability of getting the second black, given that the first one is 26 out of 51. And finally, what is the probability that the third one is red, given that the other two were chosen? Well, now you've taken 2 cards out of the deck, so there are only 50 cards, and you've taken one of each color, 1 red, 1 black, so there are only 25 reds and 25 blacks left in the deck, so the probability that the next one is red is 25 out of 50. And according to the product rule, all you've got to do is multiply those together. Given your answer as a fraction, if you just multiply straight across, you'll get 16,900 divided by 132,600. Now you can simplify that any way you want to. In fact, you could have gone back up to the top and simplified 26 out of 52 as being 1/2 and 25 out of 50 being 1/2, and you could have gotten a lot nicer answer. But as I said, WebAssign really doesn't care. But if you did want to simplify it, you could get it all the way down to 13 over 102.